Welcome to Homework Lib.
Hi, so here we're dealing with the equilibrium of formic acid in aqueous solution that is going to produce the associated anion plus hydronium in aqueous solution. This is plus water. Okay. So first of all, we know the initial concentration. So what we're going to do is using our ice table, I'm going to omit the values for water because it doesn't matter. Water is liquid, it's a pure substance, so we don't take that into account. The initial concentration that we're going to get for HCOOH, this formic acid, it is going to be 0.15. And let's assume we have 0 and 0. Let's assume that we have a change of minus x that is going to react. So plus x and plus x is going to be produced on each of those sides. This means that at equilibrium, we're going to have 0.15 minus x, x, and x. Okay. With this, we can write down our acidity constant, which we need to remember that is HCOO minus times H3O plus divided by the concentration of our acid. Replacing the values that we have, it would be x times x divided by 0.15 minus x. Okay? Here we're also already given what is the value for the acidic constant. So this is 1.8 times 10 to the minus 4. This is going to be equal to x squared divided by 0.15 minus x. So next up here, we could solve the quadratic equation that comes from this. You pass the denominator to the other side, and we get the final result. But in this scenario, what is going to happen is that we can assume that x is going to be much smaller than 0.15. Why we can assume that? If you look at the ice table, that value for x is going to be equal to the concentration of H3O plus. So for x to be in the same order of magnitude as our initial concentration, we would require for x to be of around 0.01. Okay, and for that to happen, that would imply that we have a pH lower or equal than 2, which is not going to be possible for this acid because well, it could be possible depending on the concentrations that we have, but in this case, it is not going to be a good approximation. Okay, so what we're going to do is solve it both ways. First of all, I'm going to show you the result if we solve the quadratic equation. So by solving the quadratic equation, the result that we get is an x equal to 0.005. Okay? If we use that x, and remember that this is equal to the concentration of hydronium, plugging this into our value of pH equals to minus logarithm of hydronium ion, we get a result of 2.3. Okay, so now let's do it using our approximation. If we know that 0.15 is much larger than x, this implies that 0.15 minus x, it is going to be approximately 0.15. And this approximation is used in most of the cases for this type of weak acids because we know that the dissociation it is going to be quite small. So our equation turns into x squared divided by 0.15. Thus, x is going to be equal to the square root of our acidity constant times 0.15, that was our initial concentration. Maybe you remember similar expressions in books where they show it like this, Ka times C0. Okay? So using this result within the approximation, our value for x then is 5.19 times 10 to the minus 3. Just to add more significant figures, the result without any approximation is 528, and this one is 519. Okay? And this gives us a pH of, again, this is minus logarithm of that concentration, that is 5.19 times 10 to the minus 3. That gives 2.28, which is approximately 2.3. So the approximation is valid, and we can use it. So in both scenarios, the result is 2.3 as pH.